Thanks very much. It's a pleasure to be here, particularly because for the last few months when my friends have asked me what I'm writing about lately, and the answer has been industrial software, their response is usually like, well, it's been great to see you. And I'm just going to walk away. But now you're captive, and so I get to talk to you about industrial software, and you'll see that it's actually extremely exciting. We just put out this research report last month on the industrial internet. Software, intelligent software of the sort that we're all used to on the web, and big machines coming together. You can download it at this URL. It's free, and it's also on Amazon and iTunes and Google Books and so forth. There are a lot of different ways of talking about the industrial internet and the evolution of software intelligence on machinery, but the most exciting one, I think, is the access story. This is all making the physical world, the physical world of heavy industry, of big machines, accessible to anyone who can learn a bit of the interface, a bit of the process of building software. You don't have to have expertise in the underlying complexity in the way that you used to. We see this as analogous to a handful of bits of evolution in the software world over the last few years, one of which is abstraction, which a few of the earlier presenters used. This is assembly code, which comparatively no one knows how to do anything with. It's very difficult to deal with. It's basically putting bits into memory in a computer and operating on them. All of this text does nothing but print hello world on a particular kind of processor, on a particular kind of operating system. Instead, what we all use is abstracted high-level software that takes the mess that you saw on the earlier slide and turns it into a process that is completely human in its structure. Anyone in this room, even if you don't know anything about software, can tell exactly what this code does. It adds 1 and 2 and prints what should be 3 on the computer screen at the end of it. This has taken the language, the processing logic of a computer and turned it into something abstract that humans can understand and that is human in its sort of structure. And the other big thing is modularity. We have R, for instance, which is a statistical programming language, has been around since the early 90s, and now it has more than 4,000 modules available to it. Modularity means that you can take advantage of the work of other people, take advantage of processes that hide the underlying complexity in what you're doing. If you're an epidemiologist, you can download and use epidemiological statistical models without actually having to know how to program an epidemiological statistical model. You can just download it and combine it with other modules, and they work together really well. So it becomes easy to do things where you don't have to understand the underlying process. This became very powerful on the web, and Google Maps is the standout example of modularity in the consumer internet. You don't have to know anything about cartography to have or interactive application building in order to have a really sophisticated map on your website. Your principal concern can be like cupcakes or something, but you still have an incredibly sophisticated map as part of your application. And you can take these and combine multiple services at once, join them very loosely to create things that are genuinely useful and very complicated, like this live map that shows buses in San Francisco that's several services working together at once, coupled together very effectively by someone who knows how to use a data stream from SF Muni, the bus operator, and the interface for Google Maps, but maybe knows nothing about bus operations or the process of building an interactive map or anything like that. So it's very easy to use this sort of abstract modularity to build something without being an expert in the underlying technology. And now that is coming to the physical world. We've seen this in the hobbyist area. This is an Arduino, which is a microcontroller that sells for starting at around $20 for some versions. They're very easy to use. If you know anything at all about programming, you can, in the course of a weekend, do some really impressive stuff with this. It's an interface between the physical world and the sorts of software languages that we're all very used to and that are very easy to learn. And the sort of change that the Arduino brought about, which makes sort of small the small physical world accessible to hobbyists is also making the big physical world, big machines, accessible to people who have a sort of a software mindset, a software outlook, but not necessarily expertise in the underlying engineering. And what we saw, for instance, with Dash and with OpenXC is precisely this. Ford's OpenXC program opens up the drivetrain data from a car to any developer who knows something about Android. That's all it takes. You don't need to know anything about the complicated data bus in the network. You don't need to know anything about how the car actually works. But if you have some insight into optimizing a system at an abstract level, then you can add something really meaningful to a car, as we saw with Dash, for instance. So these programs are read-only right now, which means that you can build an app that advises someone, that coaches someone that their driving is inefficient or that they need maintenance or something like that. But you can imagine that it won't be very long before write access is pretty common for this sort of thing as well. So when you get in your car, perhaps I'd like to save fuel, so I have an app on my phone that I plug into my car and that changes the shift points in the automatic transmission and changes the fuel-air mixture, maybe blunts some of the acceleration capability in the car and gets me better fuel economy. Someone else who wants a sportier drive can affect the same changes with a different app in the car. And so you're not only bringing your own preference profile to the car, you're also bringing your own computational platform, your own sort of algorithms to operate the car as well. And at the very high end, the very most complex things in the world have also become sort of abstract bundles of standardized interfaces. The Boeing 787, like all modern jet airliners, has a slightly modified version of Ethernet that ties together all of the electronic components and sensors in the airplane. It has like IP-addressed jet engines, which doesn't mean that they are IP addressed on the public internet, just that, which is a good thing, but that they are accessible to other systems on the plane. So it's no longer a straight wire that goes from the throttle control next to the pilot to the jet engine. The jet engines are on a network, the throttle is on a network, the autopilot is on a network, all sorts of monitoring tools are on the network. They all have very carefully constructed access to one another. And so the 787 in a typical configuration will generate something on the order of 1 gigabyte of machine data that's useful every hour of flight. Obviously, it generates much more than that, but a lot of airlines have sort of decided that that's about what they'll keep and that that's what's useful. And then that can be used to also sort of go back in and operate the airplane as well, the insights that you get from that. So the way we're thinking of this space in sort of how those last 3 slides laid this out, and don't study this too carefully because it's just it's sort of a brainstorm at this point. But there are all of these areas of interest within the Internet of Things, within the way that software and the physical world are coming together. And they exist at varying levels of accessibility. So on the left side of this graph, you see the maker area, things that are accessible to hobbyists, essentially. I mean, you can, some kinds of building controls. If you buy an Arduino at Radio Shack tonight, then in like 3 days, if you know something about writing software but not much about electrical engineering, you can have created a service that turns the lights on and off in your apartment through a web page on your smartphone. It's ridiculously easy, and it's very accessible then to people who know about software but not about like other sorts of engineering. And on the right side of this graph, you have things that are still really the province of like the IEEE, the hardcore engineering sort of efforts, electrical distribution and some kinds of industrial controls and things like that are still hashed out at engineering conferences. But in the middle is this really broad and exciting area where anyone who has a particular sort of outlook and a particular way of thinking about these challenges can bring really innovative ideas to the physical world. Anything from robotics to aviation and drones or changing the way that we operate our cars. This is not to say that that Boeing will someday release an OpenXC for its airplanes that lets you like plug your Android phone into a 787 and make it get better fuel economy or something. the idea is that there's this shift, and big software companies like Google and Amazon and Microsoft and Yahoo all have an enormously powerful arsenal of software and computational tools, machine learning, ways of handling these the enormous data streams and the complicated computation that has to take place to operate in the physical world, and they'll have more and more to add to things like airliners in the coming years. So while a hobbyist will increasingly be able to control her car, Google engineers will increasingly have something to contribute to a passenger airliner. Consider, for instance, that the leader in driverless cars right now is Google, which is not a car company, but they took the challenge of building a car that drives itself and they abstracted it into a software challenge of the sort that Google is very good at solving, and they managed to solve it, or start to solve it, in a very promising way. So the reason that we're excited about this is that it offers an opportunity for software people to contribute something really meaningful to big problems, things like energy efficiency, reducing impact on the environment, safety and security, making the world more comfortable, improving economic competitiveness in the developed world. It's a terrific opportunity for people who know something about optimization and general sort of machine intelligence to do something really impactful in the physical world. Thanks very much.